You can see my screen, I guess. Okay, it's gone. Just
Yes, it's visible. It's visible.
okay, okay, yeah, great. Okay, yeah, then we'll discuss some questions related to week 5 lectures. So, how was the week 5 for you?
It was continuous, it was continuity about the stereogeometry, right? So it was good. Like I first by seeing videos one time I wasn't able to catch much, but when I saw second time I was able to catch more.
Okay, that's good.
Yeah, and I wanted one clarification. Like sir mentioned, like in previous videos also, there was a point like minimum of 4 point correspondence and 7 point correspondences were there, right?
Mm-hmm. Yes.
So what does that mean? Like what I understood is first, like at first I understood like if we take two images and then we can take any 4 point correspondence means four like the pixel coordinates in one image and the pixel coordinates in the second image will take as 1 point correspondence.
Mm-hmm.
So similarly we'll take 4 points. But another time like I thought like as you mentioned like I had asked about the stereo geometry example, right? So in
Mm-hmm.
the last week, so you said that why two cameras are there. So then I got to know that is it like because of the point correspondence means like the points in from first camera and then the second camera.
Yeah.
So is it like that or the images one?
So it's like the points in the first camera which relate to the same 3D point in the second camera. That's
Second camera, okay.
yeah. I mean they represent the same 3D point. That's what we
Yeah.
mean by
So
correspondence.
that those two images one is wrong, right?
Two images means
Like if we want to compare any two images like that, I got confused. So
okay, okay, okay. Yeah,
So
got
it's about the two cameras from like the two camera centers. If we take any 3 points from those camera, then based on the pixel value, we'll do some computation, right?
you. Yeah, three, not four, I guess. At least four.
Yeah, yeah, four. Yes, thank you. That's all.
Four is for homography. Yeah. Four is for homography.
Huh.
Yeah, yeah. Okay.
Yeah.
Okay, yeah. So we'll start with the first question. We are given two projection matrices, P and P prime, and a set of corresponding points on both the cameras. I mean, they are just given one set corresponding point. So this turns out to be, I'll write it in homogeneous coordinates. So compute the line perpendicular to both the directions found by those points with their respective camera centers C and C prime. So is the question clear? Can anyone tell how to proceed? So we have two cameras with camera centers C and C prime and the projection matrices P and P prime. Anyone has any idea how to do? So if I represent these camera matrices as mm for P and m prime and small m prime for P prime, what is it that we want to do? So what we want, we first need to find these directions D1 and D1 prime. Okay. Once we find these directions, we need to get something which is perpendicular to both these directions. So there is another direction which we need to find. Let's call it as V for instance. So that V should be perpendicular to the directions D1 and D2. So that's the perpendicular line that we would like to estimate. How can we get D1? Okay, what does the D1 mean? If you remember anything from the lectures, it's done from the camera geometry part.
Direction of the Z coordinate.
No, no. D1 is yeah, D1 is the direction, but it's not for the Z coordinate. It's the direction in which this ray is going. How do we get that direction? So okay, so if we check the simple camera projection equation, so we have something like this, right? This is Ex. Okay, so we want to find the equivalent point at infinity. So x infinity is the point at infinity. We know that point at infinity gives the direction in which that ray is going. Okay, so given that information, how do we do it? So so for p we can replace it as m and m, and point at infinity it will be like d and 0, right? This is 4 cross 1 where d is a 3 cross 1 vector. So how would d look like? So x equals to md.
M into D.
Yeah, so d is m inverse x, assuming that m is invertible for the time being. Okay, so similarly we can, so what do we want? D1 equals to m. Yeah, so based on our conventions it should be m1 inverse x1. D1 prime equals to m1 prime inverse x1 prime. Okay, so given these things, I hope you understand that this is m and this is small m, this is m prime, and this one is small m prime. That's how we define our projection matrices p and p prime. And if you just place it and solve for it, what do we get? We get some weird number. Okay, I'll just write for d1 something like this. And x is what? X1 is. So if we just simplify this, we get something like 12 minus 34 minus 32. Okay. Similarly for d2, if we just replace the values, I'll just directly write the answer. 4 12 minus 8. So what did we get till now? Or rather, I'll put it as d prime, d1 prime. So we got the two directions here. Yes. Now how do we get the perpendicular direction v? Perpendicular to both d1 and d1 prime. Mm, so we are given two
Cross
directions.
product.
Yeah, yeah, exactly. We are given two directions in 3D space. So to get the perpendicular direction to both of those directions, we take the cross product. So what does it mean here? V is d1 and d1 cross d1 prime. Okay. So the usual way, if we do it, I'll just write out the numbers. This leads us to some answers. So this is the direction in which, if you make a line, it will be perpendicular to both d1 and d2. So v is perpendicular to d1, v is perpendicular to not t2, it's t1 prime. Okay, is this question clear? Of course, now we need to specify a point, starting point to which this line will happen. So in general, we write a line. I mean, you can write a line something like this, right? In 3D space, x is rather x tilde. I would like to put it this way, given the conventions. So there will be a starting point plus some scaling factor times the direction. The scaling factor will belong to all the real numbers. So now we got just this point, but we have to find any line that passes that is perpendicular to both the directions. So given this, we have specified this, and if someone wants a specific starting point or a point through which it should cross, we can just specify x naught tilde in that way. Okay, so is the first question clear?
The x naught tilde.
Yeah, x naught tilde at this point, it's not specified in the question. They just asked us to
Okay.
find a line perpendicular to both the directions. So it doesn't mean that you have to pass through any specific point. That's why I'm not specifying x naught tilde.
Okay.
Okay, then if this is fine, we'll move on to the next question. By the way, just to note, we can take, if v is a valid answer for this, then any multiples of kv is also valid for this, or k belongs to r. Similarly, the scaling factor will also be scaled. So if you have multiple choice questions, then v and kv both will be the correct answer. Okay, so we move on to the next question. We have a plane induced homography H between left and right image planes. Okay, hopefully this time I'll be able to use shapes properly. Okay, this will like this. So these are the two cameras, and then if we have a plane in the scene, this is the scene plane. We have camera center C prime, and yeah, some point X. Okay, fine. Okay, so what's the question actually? So we are given plane induced homography H between the left and right images of a stereo set. Stereo means we have two cameras as usual. Uh, so we are given H and F. Find out whether they are compatible or not. How do you do that? Any idea? Okay, what do you mean by compatibility? Both of them should represent the same relations, right? What kind of relations can you get from fundamental matrix? So if I have a point x here and a point x prime here, what is the relation that fundamental matrix gives us?
The point can be like we can map point and epipolar line.
Yeah, so if we use fundamental matrix F, we get some line like this using mapping F, right? And what's the mapping that we get from homography? Homography is a
Point
point to
to
point.
point.
Yeah,
Yes.
homography is a point to point map. And this is point to line. Okay, fine. So given these two things, can you relate these two things? I mean, okay, we'll just try to write out the equations. X prime equals hx. That's one of the relations that we have from point to point mapping using homography. And x prime transpose fx equals to 0. This is the point containment relationship. I mean, this is the L prime, equivalent L prime, the line, epipolar line in the second image or the right image. Okay, so given these two things, can we do anything about it?
Now we can replace x prime as hx in the
Yeah, yeah.
second fundamental.
So it will be like hx transpose fx equals to 0. Okay, so what does this mean?
X
X
transpose
transpose
h
X
transpose
transpose
f.
fx equals to 0. And when it is valid?
When h transpose f is skew symmetric matrix.
Okay, how do you say that?
Because the general rule for the skew symmetric matrix is like if S is a skew symmetric matrix, then we can take any x like valid value of like valid matrix for x, and then the equation that form like using x transpose Sx will be always zero.
Okay, you're just missing out a small point in that. So it should be for all values of x.
Okay.
If this happens, then only you can say that. So here this happens to be the case. You just take any point in the first image and get the corresponding homography and fundamental matrix. Given that you have this scene plane, then this equation always satisfies. So given that it's for all values of x, as you said, uh, skew symmetric matrix have the property that x transpose Sx equals to 0. X is a vector, by the way. Vector for all values of x. So it is if and only if property. What do I mean by that is if this thing holds, then it's a skew symmetric matrix. And if you know that it's a skew symmetric matrix, then this thing holds. So it's an if and only if property. So if you know that this holds true for all values of x, then it's a skew symmetric matrix. Okay. Can you intuitively tell me why does it hold true for 3D vectors and matrices? Any intuitive idea?
No, sir.
Okay, okay, we can just try doing that. So for this question, so you know that every skew symmetric matrix can be written like this, right?
Yes, sir.
Yeah, that was given in the class. Okay, so V is some three element vector, and S is something, yeah, the skew symmetric form of that. Okay, so we just try to expand this. X transpose V cross X equals to 0 in 3 dimensions. This holds, right? So what does V cross means? We are just trying to take a cross product, right? So first we take cross product of V with X, and then we again try to multiply this with X, take a dot product. So what kind of product is this? Scalar triple product, right? Since we are getting a scalar value 0 here, we call it as a scalar triple product. So in this specific case, it is 0. Why? We have v here, we have x here. V cross x will be somewhere here. Do you agree with that? V cross x will be perpendicular to both v and x.
Yes, sir.
So now this, if it's perpendicular to v and x, then the angle between this and x is 90, right? So this is 90. Even this is 90. If this angle is 90, then what more can you say about it? Dot product is like cos theta. It's proportional to cos theta, right? So x transpose of some vector is, that means we are taking dot product of this x and this v cross x, these two vectors. Do you agree with that? Okay. So at least do you agree with this formula? Cos theta between two vectors looks something like this from matrix linear algebra.
Yes, sir.
Yeah.
Yes.
So that means what? So we are, if you are taking transpose A transpose B or X transpose some other vector, it means that we are taking a dot product. I mean, so it will be proportional to cos theta, right? So cos theta means the angle between V cross X and X is 90, which means that it will be 0.
Okay. Yes. Yes.
So if cos theta is 0, that means this whole dot product is 0, right? I guess you understood. That's what I.
Yes, sir.
Yeah, okay, great. So if this is the case, so this holds true for three element vector. I mean, just an intuitive idea why it should hold true. Okay, where are we? So ultimately, we are in the question that we need to see whether H transpose F is Q symmetric or not. So other way to write Q symmetric is H transpose F equals to minus of F. Okay, it should be H transpose F whole transpose. That's what Q symmetric definition gives us. Okay, so we will not check it like that. We'll just directly place the values. So this is H transpose by the way, which leads us to something like this. Okay, just seeing this matrix, can you say it should be a skew symmetric or not? This multiplication.
I guess no.
Yeah, just try to multiply the first row and the first column here. So it gives something like 29. Okay. So is it a valid skew symmetric matrix? The
No, sir.
diagonal element having some non-zero value? No. Okay. So here itself you can say that it's not skew symmetric. So it's, I mean, it's not compatible. So I'll just
And
change.
even no negative values are also there.
Yeah, that's even a better way to check it out. Yeah, you need some negative values to cancel out to get the zero diagonals. Yeah. So given this, it's not skew symmetric. So okay, so F and H given are not compatible. So I hope the core idea is clear. What do we mean by compatibility? It's just that these equations should be satisfied. That's all. Okay, so we move on to the next question then. So we have okay, so they are just trying to give the convention. What does it mean? So if you have some matrix like this is the 1 comma 1th element, and this is the row index, and this one is the column index. That's all. Okay, plane induced homography H between left and right image planes of a stereo set imaging setup is given by this homography. Again, we have some plane induced homography. Okay, okay. Given these,
The rectangle is like any plane objects in the
yeah, yeah,
like in
yeah,
the scene,
yes,
so
yes,
it can be considered as a book or something like that, right?
yeah, yeah. Book, wall, whatever you want.
Wall, yeah, okay, okay.
Anything, table, top of the table, something like that. Plane. Just write it as C. This is a scene plane. Again, we have homographies given to us. So we have homography H and 2 point correspondences. We are given x1 here, x2 here, x1 prime here, and x2 prime here. Okay, where x and x prime are the 2 points on the left and right image planes. So x1 corresponds to x1 prime, x2 corresponds to x2 prime. Compute the fundamental matrix F corresponding to this stereo imaging setup with the element of the third row and third column of F to be 1. Okay. How will you compute that? Any idea?
Homography is given, so we need to find the E prime, the right epipole.
Okay, okay. Why do you say that? Because F is
F is eh,
E prime
yeah,
cross H, right? So we know the
yeah.
H. We just need to find the E prime. How can you
Find the
find
E
E prime?
prime. Uh,
E prime is if you have two lines.
L1 cross it. Yeah.
If you have two lines in the right image plane, then you can just take a cross product. So the point is now how to find L1 prime, L2 prime. How can you find that? You're given homography, right? Can you use it? Yeah, so if we have 2 points in the right image plane, then we can just take a cross product and get that, right? How can we get 2 points in the right image plane? Like this.
Okay. Yeah.
So this will get 1 point in the right image plane, and we are given another point in the right image plane. So given this, we get L1 prime. Similarly, L2 prime is this. Okay. Okay. Yeah. So given this thing, uh, we'll just replace the
Uh,
matrix.
X1 prime is actually HX1, right?
Yeah, I was also thinking the same, but Okay, okay. So yeah, so here the point is you don't the scene contains other elements as well. If you
Yeah.
remember the last 2 or 3 lectures, so the scene contains a plane where through which you can get some homography, which is fine. But these
Okay.
points do not belong to the what do you say the plane correspondences. So these are some other point correspondences. For instance, it's like x1 out here, which do not lie on plane. Okay. So if you're given such correspondences, then you can apply this thing. Then actually hx1 and x1 prime won't be the same.
Okay.
Okay, because h will say according to the scene plane, but x1 and x1 prime are some other. I mean, they are not derived from that plane. They are coming from uh, some other scene point which doesn't belong to the plane. So since you don't belong to that plane, we just want another point here which will lie on the epipolar line. That's all.
Okay. So the edge here is different from the edge we have seen earlier. Like
Yes,
it's
yes. In the
taking.
second question, it's different. In this question, I mean, it's a edge for sure, but it's only for a part of the
Okay.
scene, for not for the whole scene,
Okay.
because that's what they have written it. Yeah. Homography between left and right image planes is given like by this, and 2 point correspondences are given. Okay. Yeah, because if you try hx1, it won't be x1 prime.
Okay. So like in the previous at the beginning of the stereo geometry, we have seen that like if we consider x, then it will be hx1 will be equal to x1 prime,
Yes,
right?
yes, yes, yes.
Okay.
So yeah, when we write x1 prime is hx1, that means we are considering the whole scene as plane. So in general, we are writing here the whole scene is not planar, only a
Okay.
part
It's
of the scene.
specific from the
Yeah.
like the plane
Yes.
induced plane.
Yes. 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 Okay. So we'll just write out the numbers. So if we now know these things, L1 prime will turn out to be minus 2, 34 minus 24. L2 prime will turn out to be, these values are given, right? Yeah. Okay. Okay. So these are all in homogeneous coordinates. So given these things are in homogeneous coordinates, we can this will turn out to be minus 3686 minus 40. Now given L1 prime, L2 prime, we can get E prime as we saw earlier, which is a big number 636 780 1052, and then we can just place the homography from the question and E prime here, which will give some big answer. Okay, so is this question clear? I mean,
Yes.
the idea of the question is clear, right? Yeah, numbers are fine. Okay, so here there will be some other x2, rather hx1 will come here and hx2 will come here. Okay, yeah, fine. Mm, okay. Okay, I guess the next question is the most interesting question for today because this was left as an exercise in the class. So you're given two camera matrices P and P prime, and you need to find the induced homography from the plane at infinity. Do you know the formula? How to find the homography from plane at infinity? So in general, we have general camera matrices here, which I will write it like this. So do you know the formula?
No, sir.
Okay. It was given in the revision part, the last lesson.
Yeah, summary part. Yeah, even
Yeah,
I saw it.
and it was told that we should try it out.
Huh.
So I think we doesn't include me, I guess. But anyways, I tried it out and then I have to give the answer because I need to solve this. Okay. So in general, if you know that this is I zero and then this is P prime is M prime, then the homography at infinity is M prime, right? So I'll just give you an intuitive answer for now, and then we'll derive how to do it. So since
Okay.
it depends on these matrices only, so H at infinity in general will be M prime M inverse. That's all. So we're just trying to make it identity somehow. If you make this identity, you have to compensate for that here. Okay, we'll prove it. How does it even come out? Okay, yeah. So today it's full of planes. Okay. So what I will do is I'll call this as plane at infinity. How do the points at plane at infinity look like?
The last, like last one will be zero.
Yeah, yeah, that's true. So the plane at infinity is something like this, if you remember correctly. So so all the points will have the coordinates like this, so that this into this is zero. This is just as a side note. This part is clear, right?
Oh, yes.
Okay, great. So this is the vector which represents the plane at infinity, and then these are the points. These are the points at infinity. Okay, okay, this is fine. Coming back. So since we have these things, mhm, I will remove these because these are problematic for my case. Style. So what are these points? This is E prime and this is E, right?
Yes, sir.
And this is C and C prime camera centers. It's becoming clumsy, but I hope it's okay. So this part is fine. Okay. Coming back, what do we need to do? We need to find this H pi, which is H at infinity for our case. Homography induced by the plane at infinity. Okay, as simple as that, we will go back to our favorite projection equations. So how will you find this point at infinity? So first we'll find the point at infinity. How will you do that?
P into X.
Yeah, of course. We have p into x, but uh, we know only these points, x and x prime, right? we need to find the point at infinity x. So we will go back to our projection equation, and p will write as mm, and x will be like d0, right? That we did slightly, I mean, 2 questions back, I guess. So
Oh,
given
yes, sir.
this, our point at infinity, which we represented as d0, will be given as m inverse x and 0, right? So we are trying to find,
Yes, sir.
image this point at infinity onto the two image planes x and x prime. That's what we did till now. I mean, yeah, that's what we did. Okay. So again, I would try to do that same thing in the second image. But since we have the expressions, what should I do? I just replace it like this, right? What does this give us? Mn inverse x, right? This is,
That is M prime, right?
oh, sorry. This is m prime, m prime. Yeah.
Yeah.
So this is m prime, m inverse x. So this h infinity is m prime, m inverse. Since we are relating the two coordinates directly, is this fine?
Yes.
So this holds for all values of x, by the way. Since for every value of x, we can find a point at corresponding point at infinity on the plane at infinity. Once we have the point on the plane at infinity, we can just project it back onto the second plane. So this is done, I guess. So okay, we'll do the extension as well. We were asked to find the fundamental matrix in the summary part. We'll finish that as well. So how do we do that? Any idea? Given that we now have h infinity. It should be simple now, right?
Yeah. So the X transpose H infinity transpose F and X will be equals to 0.
Yeah, so the whole thing is about finding the epipole E prime, right?
Yes.
Yes. Okay. So what's out there? So if we find the epipolar line, which is some cross product of epipole and the point, then we are done. And we know x prime is h infinity into x, which is m prime m inverse, or I'll use this notation now, x. Okay, so we just need to find E prime. How will we find E prime? What is E prime? Image in the right,
Right. Right epipole.
I mean, image of what? Image of first camera center, right?
First canvas. Yeah. Yeah.
Okay, so how does it look? P prime C, right? So C can
Yes.
be written as C tilde 1 by our convention. And what should be C tilde? Okay, I guess we have to revise these things again. Okay, KR, if you remember, it looks like this, which I am denoting as, which again I am denoting it as M and M. So if I take M outside, it should be M inverse M, right? So
Yes.
comparing these two
My
equations, what will we get? C tilde is,
minus M inverse M.
yeah. So I hope this was done. Even we did it in
Yes.
some of the sessions. Yeah. Okay. Fine. Yeah. Just cross verifying that it did not miss out on this. Okay. Great. So now we have every element that we need. We have P prime. We have C. C is given by this, right? If I write it properly, M prime. If I do any mistake, please let me know. Okay. So this turns out to be like this. Okay, minus. See, now I did a mistake. Okay. So So this is what? If you just multiply it properly, minus m prime m inverse m plus m prime. This is what E is. So F is E prime cross m prime m inverse, which is this thing, m prime minus, all are m's here. I have to write it clearly. M minus m prime m inverse m. Oh, this is m prime. Yeah, I'm just rewriting this out here. Into m prime m inverse. So this is fundamental matrix for general projection matrices P and P prime. Is this fine?
Yes, sir.
Yeah, this is what was given as an exercise. So our question was just to find h at infinity, which is just m prime m inverse, which, okay, all these numbers are there. M prime will look something like this: 2, 2, 3, 3, 5, 7, 1, 3, 9. M inverse will be something like this: 1 by determinant of m, 0, 5 minus 5, 0 minus minus 10, minus 7, 7. Okay, if we try solving this, we'll get something. That's all. Okay, is this
Yes,
question
sir.
clear? Yeah, the
Yeah,
main
yeah.
part is the derivation. So, what we did is we just take, we are given 2 point correspondences x and x prime. So, what we try to do is we try to find the point at infinity, and with finding this point at infinity, we come back to the other plane. I mean, yeah, the other image plane, x prime. Relating these two things, we get the homography at infinity, and then for finding the fundamental matrix, we know that we need to find the epipole in the second image plane, which is nothing but image of the first camera center onto the second image plane. So if we just do by comparison, we can get the first image camera center. If we get the first image camera center, we just try to get the image onto the second image plane, which gives us this expression. Once we get this expression, we just replace it, and then we get the general fundamental matrix expression. Okay. I hope the core idea is clear. Okay.
Yes, sir.
Okay, that's fine. Uh, this is a different question. So we are done with projection matrices, hopefully. Okay, given affine homography of affine homography HA, okay, and a point correspondence x and x prime. Yeah. We have x1 and x1 prime given to us. We are given HA as affine homography. Do you think it's affine homography? Is it correct?
Yes.
Why do you say that?
The last row is zeros. Oh,
Yeah, last row is 001, so
one.
it's a affine homography. I mean, it's an affine transformation. You can just say it as affine homography. The same. Okay. What do we need to find? Again, fundamental matrix. So by now we remember the whole formula.
Yes, sir.
It is something like this. I'm just writing it for namesake. We are given HA. How will we find E prime? How will we find E prime? Hmm?
E prime is like above, same as above video.
Okay, same as above. We don't have any projection matrices here. How will you do it?
Okay.
Simple, right? We are given point correspondences again. What's Whenever you're given point correspondences, you can make use of that. You are given some x1 prime out here, you are given x1 here, you can map it here with hx1. For our case, it is ha times x1, right? And then what? L prime is
X1 prime cross Hx.
I. This is it. So once we get the epipolar line, then what? Okay. Then comes the main question. How do we do it?
Fundamental matrix.
Yeah, we need to find the fundamental matrix, for which we need to find E prime.
E prime.
How will we get E prime? Do you remember any property of the fundamental matrix given by the homography? Sorry, for affine homography. How does fundamental matrix look like for affine homography? I mean, looks like a matrix, but what?
0 0 A.
Yeah,
A B C D E.
so it depends on what property you follow. It's written like this in the notes, so I'll follow that. Okay. So any information that we have with this matrix? How do we find epipole of a matrix? F into E is 0, right? This gives us
Yes.
what? E is left epipole. And F transpose E prime, or rather I'll do it the other way. E prime transpose F is 0 transpose. Here 0 is 0 column vector, and this is a 0 row vector. E prime is right epipole. So this is just a general definition of epipole. So with this given specific structure of the matrix, what can we do? I'll just try to find these epipoles. So it was said in the class that these are the properties of the matrix. So I'll write it as E1, E2, and E3. Okay. So which gives us what? A E3. This is B E3, and this is what? E times E1 plus D times E2 plus C times E3. Simple matrix multiplication, right?
Yes, sir.
Yep. So if you just see these first two elements, they don't depend, not dependent. Okay. Uh, I should write it in a different manner. Okay. Just give me. I'll write it in a different manner so that it's more clear. So if you have any point on the left image plane, we can directly multiply f into e, right? So this is f and this is x. What we get is L prime. Is this fine?
Yes, sir.
Yeah. So it is ex plus dy plus c. So this L prime, what is this that we, what is it that we are observing? That it is not, the first two elements are not dependent on values
X and Y.
x and y. What does it mean? So for any point on first image plane, we will get the first two elements to be same as a and b, right?
Yes.
Which means what? All epipolar lines, which is of the form L prime transpose x prime is 0, All epipolar lines are parallel, right? A and B are same.
Yes, sir. Yes, sir.
All epipolar lines are parallel since A and B are same, right? So similarly,
Yes, sir.
even for the other plane, when you try to do x prime transpose f equals, you get the d and e, I guess, or rather, you get something like this: e d ax prime plus by prime plus c. So again, in the left image as well, we get, so this gives us L. So in the left image as well, our epipolar lines will be parallel. So this is the property that was told in the class, that epipolar lines will be parallel. Given that they are parallel, what can you say? Where do they intersect? They intersect at what? At some point at infinity, right?
Yes, sir.
Epipolar lines will intersect at point at infinity. And what would be that case? So given that I have L prime something of this sort, A, B, and some value, something else. Okay, P, or rather L1 prime and L2 prime, some A, B, and Q. What would be the intersection? Simple cross product, right? And what does it give? We have done this in the first class, I guess, first session. What does it give? B times Q minus P. Here it will be A times, what is this? P minus Q, and this is 0, right?
Yes, sir.
So we have B minus A 0 as our intersection point. Okay, it should be Q minus P. Okay, so this is the intersection point, and we know that scaling doesn't matter since we are in projective space. So we take this as our intersection point. And what do we want? E prime. A is L1 prime cross L2 prime, right? Which is nothing but B minus A 0. So our epipoles also lie at infinity. Is it clear?
Yes, sir.
Yeah. So for homographic transformation, our epipoles will lie at infinity. Our epipolar lines will be parallel. Yeah, these are the properties that were discussed in the class. So, so once you get L prime, which is using this, okay. So our question is this, right? So once we get L prime, which if I say that contains elements like this L1 prime, L2, okay, so L2 prime and L3 prime, our epipole will look like this, right? L2 prime minus L1 prime 0. Yes?
Yes, sir.
Yeah, so given this, we just can now compute the fundamental matrix. So our epipole will somehow, okay, our L prime will look something like this if my calculations are right, that you can check it out doing it yourself. So our epipole will look something like minus 3 minus 13 0. And then this is nothing but, we try to put the skew symmetric form. matches something that we are given. 1357001. Okay, which will give us some answer. And how should that answer look like? We clearly know that the first, this left four elements will be zeros, and the others. And if you remember more, this will be equal to the epipole. These two elements will be the part of epipole in the right image plane. This will turn out to be the epipole in the left image plane. These two elements. These will part of right prime. This will be a part of left epipole. So whatever line you see, right, 13 minus 3, it will just be a scaled version of it, or yeah, here it's negative. Okay, I hope this part is clear.
Yes, sir.
Yeah, definitely. Okay, I have some interesting question. This is not that interesting. Okay, this one looks different from the kind of questions that we did. This is a quick question actually. So we have a matrix A for which the following SVD decomposition is given. Okay, so first question is, do you think that this SVD is correct? I mean, someone gives it to you doesn't mean that it should be correct, right? What are the checks that you need to do to ensure that this SVD is correct? So we know that S is diagonal and non-negative. So it will either contain 0 or positive elements. Okay. And what about U and V? U and V are orthonormal matrices. What does it mean? That if you take, for instance, two columns and multiply them, there will be 0. If you multiply multiply means take a dot product. If you take the same column and take a dot product, then it will be 1. Okay, that means ui transpose uj equals what? 0 if I not equals to j, 1 if I equals to j. That's all. So you can check that it's a valid SVD decomposition. So we'll go through the options. The two singular values of A are non-zero. Is it true?
Yes, sir. Root 2 and root 2.
Yeah, yeah. Okay. The third singular value of A is 0. This is
True.
again true. A can be an essential matrix, or A cannot be an essential matrix. Which one is correct? What are the properties of essential matrix? That sigma 1 should be sigma 2 and sigma 3 should be 0, right? Where S will give me sigma 1, sigma 2, sigma 3, others are 0 in the singular value decomposition. Do you agree with this?
Yes, sir.
Okay, so do you see that here? The two
Yes,
singular
sir.
values are same, so it can be an essential matrix. That's all there is to this question. Okay. Yep. I guess we'll stop here. You have any other question? Then you can ask. Else, we'll stop the session.
Of recording.
Recordings are there, I guess. If you see
No,
the
sir.
Excel.
Question after recording.
Okay. Okay. Fine. Yeah. So no questions regarding to today's session. Okay. Fine.
No.
Okay then. Yeah. I'll stop the recording.